We'll start our analysis of vibrations by beginning with a little bit of mathematics review, specifically looking at Fourier Series analysis. And we're going to be doing this in a couple different ways. So in this section, we're going to cover how do we convert our analytically defined functions into a Fourier Series expansion. They'll move on to discrete data sets. How do we do a discrete Fourier transform or a discrete Fourier series on those? And then kind of going in the opposite direction, if we have some data already, how can we use a power spectral density to analyze the frequencies that are contained in our data? So let's go with a little bit of definition of what are we going to be talking about in this section and really throughout the course. So we're studying harmonic motion for right now. So kind of going a little bit bigger for now. Motions that repeat themselves, or signals generally that repeat themselves after equal intervals, we are going to be referring to as periodic. So if it's kind of a copy and paste, one after another, that's just generally a periodic motion. Now a specific kind of periodic motion that's mirrored around some equilibrium point, is going to be simple harmonic motion. So if we have something that is just like sine or cosine are great examples of this. Their average value is 0, it goes up to 1, down to -1, keeps repeating itself, but on average, it's 0. That is simple harmonic motion. Now, all simple harmonic motion is periodic, but not all periodic motion is a simple harmonic motion. But what we can do is we can take multiple of these simple harmonic motions, add them together, and get something that is still going to be periodic, but is not necessarily mirrored around the equilibrium point. But the basis of it is a lot of these simple harmonic motions. And that's what leads us to be talking about what is a Fourier series. Now, you should have seen Fourier series before in your first ordinary differential equations class, and you went about doing a Fourier series expansion of a function probably, and you also could have a definition of how to do a Fourier transform. So we're going to be focusing on doing that Fourier series expansion for now. And what you should have at least seen in your ordinary differential equations class is that you could take any time series and we could decompose it or express it in terms of an infinite series of sine and cosine terms. And that's very generally speaking what the Fourier series is we're going to add up an infinite number of sine terms plus an infinite number of cosine terms, and when we take an infinite number of them, we get back exactly our original function. Now, I will say on the surface, it seems like this is not going to be very useful, and you probably in your ODE class didn't really see the utility of it at all. We're kind of going through, we have a nicely defined function, and we're going through a lot of work to now define it in terms of an infinite sine and cosine series. But we're going to see the payoff later in the semester when we're going to see it's going to be easier to work with these cosine and sine terms than however our function was originally defined. Now, we can't, in practice, actually use an infinite number of these terms and add them all together and get back our original function. So we're typically going to be using just a partial sum, where instead of adding the first term through the infinite term, we're going to add the first, the second, the third, up to some finite limit. 100, the first 100, the first 1,000 terms, something like that. And this will not give us back our original function because we're not literally taking an infinite number of terms. But if we take enough of these terms in the partial sum, we're going to get a pretty good approximation of our original function. And we're going to be looking at ways to see, well, how close are we getting? How good is this estimate going to be? Like I said before, we're going to, in later sections, see why is this even helpful? Because we're going to see, even for these simple functions we're going to look at in this section, it's pretty time consuming to do the Fourier series expansion. So how's it going to help us? In a couple of sections, we're going to see that working with trig terms is going to be easier than working with the piecewise functions or however our function is defined. One reason for that is that trig terms, sine and cosine, are easy to differentiate and integrate. The rules are really simple of just using a chain rule on it. We know how to deal with it. So not only is it easier to differentiate and integrate these trig terms, these simple trig terms that may be our original function, but the trig terms are also infinitely differentiable, infinitely integrable. So we can, if we're starting with position, we can differentiate it to get velocity, differentiate it again to get acceleration, differentiate further if we had a reason for that, or if we had acceleration, we can integrate it up to get velocity, up again to get our position. So it's much friendlier to work with. And since we know that using an infinite number of terms, the two functions are identical, our original and the Fourier series expansion, then if we integrate both sides, they'll also be equal. Or if we differentiate both sides, they're also going to be equal. Now, on the next slide, we're going to see, again, how do we define the Fourier series and what does it look like? But as a little bit of a preview, another utility of doing a Fourier series expansion is that we're going to be finding these coefficients. I'll talk about this in the last subsection of this topic, but we're going to be finding coefficients in front of all of these sine terms and cosine terms. And the utility of looking at these coefficients is it's going to tell us about the relative strength of specific frequencies contained inside of our signal or inside of our motion. And we're going to be looking at that through power spectral density a little bit later. All right, so a little bit of a refresher of what the Fourier series was. Let's look at mathematically, how did we define this Fourier series? Now, I'll note that the way I'm expressing it here, I'm only using real terms. I'll talk about the specifics in a minute here, but these A terms and these B terms are all going to be real, and the cosine and sine are going to be real as well. There's other ways to express the Fourier series where you could use, maybe your coefficient is complex, or you are using an exponential to a complex power. Those are alternate ways to write it, but here I'm going to be using just the real parts because we're going to be able to get, I think, a little bit more of a intuitive sense of what the values in the Fourier series are telling us. All right, so let's kind of break this apart for a moment here. So if we have some generic function x of t that's on the left-hand side, if we know its actual algebraic definition, or it might be a piecewise function, whatever it is going to be exactly equal to this right-hand side here. So this a naught over 2 plus this infinite series. Right? So starting at n equals 1 to infinity. So on the right-hand side, inside that summation, we have the pieces here are going to be an infinite number of cosine terms, each one with its own coefficient, this a sub n, and then adding to that an infinite number of sine terms, each one with its own coefficient, b sub n. So notice what we're doing here. We have n equals 1 to infinity. N is only going to be taking integer values. So if we started to write this out, we would say, well, that's going to be a sub 1 cosine omega t plus b1 sine omega t plus a sub 2 cosine of 2 omega t plus b sub 2 sine of 2 omega t plus, and we're going to keep adding all of these terms together. So for every n value, we have a cosine and a sine term we're going to be adding together. And then on the outside of that summation, we have this constant, this a naught over 2. Now notice that all the cosine and sine terms are going to be these integer multiples of this omega term, or harmonics, we might say, of omega. Now for the analytical Fourier series we're going to focus on right now, that omega is going to be defined as 2 pi over t, where t is going to be the amount of time of one period if we're talking about a periodic function. So this omega is sometimes referred to as this fundamental frequency. And then we're adding the cosine of that frequency, the sine of that frequency, to then its harmonics, or its integer multiples, to reconstruct our original signal. All right, so in short, that's how we can write this Fourier series in a very compact form. But what we have to know is, well, how do we get these coefficients? How do we get these a terms in these b terms? So we have a definition for each one that you should have seen before, but we'll see it again now. So how do we find that constant term out in front? Well, we have kind of two ways that we can express it. We're really going to be using typically the time version of this, so that extreme right-hand side is what you should really pay attention to for the way we're going to be calculating these. So to find that constant term, that a naught term, sometimes called like the DC offset, we're going to take 2 over t, again, the time period of one full cycle of our signal, times the integral from 0 to t of just our signal dt, and we integrate it with respect to dt. Now we're going to come back to these equations when we go through the examples, but we want to know kind of the methods we're going to use here. Now, how do we find the an terms? Keep in mind that for n equals 1 or 2 or 3 or 4, that a1, 2, 3, or 4 is going to be potentially different for every value of n that we're using. So typically when we find an or bn next, when we actually go through this integral, it's going to be in terms of n. So if we look at the extreme right-hand side again, it looks similar to the a naught calculation, but we see here it's x of t times cosine n omega t. So typically when we go through this integration step, an n is going to pop out, and that's why we're going to see that the an's are going to be a function of n almost always. And then the coefficients in front of the sine terms, those bn terms, looks a lot like the an, but we see here we're taking our original signal, that x of t, and we're multiplying it by sine n omega t, integrating it, and then multiplying it by that 2 over t. So I'm not going to go into the details again here of where do these a naught, these derivations come from for a naught, an, and bn. You probably covered them briefly in your math class, and you can look them up if you're interested, but I'll just present them here as these are the formula we're going to use to get these coefficients. And then after we get these coefficients, we can put it all together, and then we can get the series representation of our original function, and we're going to see it's made up of constants, cosines, and sines. Now again, our focus at the moment is if we have a defined x of t, so we have some algebraic representation of it, how are we going to go from x of t to its Fourier series expansion? So these are the steps generally that we want to take. So we're going to take that original function. If it's periodic, what we want to do is let's find the period of the smallest full oscillation. And that is what we're going to use to find that fundamental frequency. Now, we could take 2 periods or 3 periods, and we're still going to end up with the same results, but I think it's easier if we find that smallest period that keeps repeating itself and focus in on that. Right? So that is how we're going to define the period t, is that amount of time. Again, use that to find our fundamental frequency. And as we saw in the previous slide, 2 pi over t is going to be our fundamental frequency. And I'll take a moment here, this omega, the fundamental frequency, and anytime we're using the omega, that is an angular frequency. It's going to be in radians per second. There will be times that we are dealing with sometimes called normal frequency or denoted by f, and that is 1 over seconds, or hertz is usually going to be its representation or the units associated with it. But most of the time we're in radians per second in our calculations. Okay, so we found the period, the smallest period that keeps repeating itself. We found the time it took for one period, and we have our fundamental frequency. Now we need to define an equation for our function over that smallest one period. Sometimes we might be given like a graphical representation of our function. Sometimes maybe we are just handed the actual equation, but we need to get our hands on our equation defined from 0 seconds to t seconds. And sometimes, as we'll see in our examples, that could be a piecewise function, or maybe it is just some continuous function that goes from 0 to t seconds. Either way, as long as we have its full definition over the first t seconds, then we can proceed to start calculating our coefficients. So then I would recommend calculate that a naught term using the previous equation where we're going to integrate x of t from 0 to t. So we have that constant term. Then we can calculate the usually formula for the an terms and the bn terms. Like I said before, typically these are going to be in terms of n and not just always the same constant themselves. And we're going to see different ways that we are able to simplify the an and b terms. We want to take advantage of this simplification. We're going to see that sometimes we'll have leftover cosine terms or sine terms that might be able to simplify into 1 or -1 or 0 as we're going to be seeing. So as much simplification as possible is going to be good. Now, sometimes simplifying it doesn't matter too much if we're going to be throwing this into MATLAB or doing stuff numerically with it, but still the less we have to write and the less taxing we have to be on MATLAB, the better. So simplify it as much as possible, as we're going to see in the upcoming examples. So at this point, we have our A0 term, we have our formula for the AN and the BN, we know our fundamental frequency. Now we can kind of stitch everything together. We can put these coefficients that we found in steps 3 and 4 together to get that full Fourier series expansion of our original function. So going back a second, at this step in our procedure, we have our A0 term, we have AN and BN. Now we can pop those values back into that top expression and put together that general expression that's going to tell us what is the exact infinite series representation of our original function. Now that we know how those coefficients are defined, we can put those up, and now that we know the value of omega, we can also put those into the cosine and the sine terms. And at this point, we'll have our full Fourier series expansion. So in the next steps, we're going to look at some examples of applying these steps and these definitions for the coefficients.